Hi, guys. How you guys doing this morning? This snowy morning. Can everybody hear me okay?
Yeah.
Okay,
Yes.
good. All right. Nobody responded when I said good morning. Just want to make sure you guys can all hear me. Okay. I know it's cold, right?
It's freezing now.
We've had a really, really unseasonably warm January, so I don't know what to tell you.
Can't complain about that one.
I know, right? Okay. All right. Before we actually talk about homework for chapter 1.3, I'm sure you guys have questions about it. I want to finish up this problem here, example 6. What I'm going to do is we're going to go through example 6 because there's something we need to talk about with this kind of form right here, this x squared plus 9. It's a special case we need to go over. And then what I'll do is I'm going to actually do this one out myself off time, and then I'll scan it in and so you guys can see what the answer is and how this actually works. So we're not going to actually cover this in class, but I'll do it out and then scan it in so you guys can take a look at it. That's the last example. And then if you have questions about that last example, we can talk about it like in office hours. So I want to finish this example first before we talk about questions for the homework, okay? Because this may actually answer some of your questions for the homework, and then we'll move on from there. Okay, so this is our lecture examples, right, for chapter 1.3. This is this partial fractions decomposition, and then after doing partial fraction decomposition, we're going to integrate, right? So the whole point is I've got this rational function that I need to integrate, but I can't integrate it in the form that it's in. So partial fractions is a tool for me to use when I'm dealing with rational functions and I need to integrate them, okay? So it's a whole process for how we need to set this up. Now we've talked about basically, let's see, just a quick recap, the partial fractions, right? So I've got our general linear factors, right? So let's see, we'll do this one, yeah. So this example here, I just have straight up linear factors here, and linear factors means I just have, it's a simple x with a first degree, x to the 1, right? And then x to the 1, you know, x to the 1 right here. So all these cases here where I have an x to the 1, okay, those are simple linear factors. This is a case long division where I've got like my numerator has a higher degree than my denominator. I have to simplify this fraction first. And then this one here, I have a repeated linear factor. X plus 2 is the linear factor, but it's being repeated twice. So I have to handle that slightly differently. Now, in our third case that I need to think about is I have an irreducible quadratic factor. So this right here, x plus 3 is a linear factor, right? I can solve for x on that one. Did we go over the lecture example 5 last class? I don't have notes for it, but I could have missed it. Yeah, okay, great. I was like, yeah, I'm looking at, I make a note about which class I'm covering here. So this is x plus 3 is a linear factor, right? Because I can solve, I can say x plus 3 equals 0. I can solve for x, right? I'm going to get x equals minus 3 on this factor here. This one here, x squared plus 9, let's just do it off to the side. X squared plus 9, set it equal to 0. Subtract 9, subtract 9. Give me a sec. I'm going to get x squared equals minus 9, and I go to solve for x, and I'm going to get an imaginary solution, right? So this has no real solution. That's what we mean by irreducible quadratic factor. It has no real solution, okay? Be really, really careful. What I see as a common mistake that people make here is they go x squared plus 9, and they think of it as x plus 3 times x plus 3, okay? If you do x plus 3 times x plus 3, let's just do it out right here. This is a common mistake. If I'm going to FOIL this out here, right? So if I FOIL this one, x times x, x squared, right? This is plus 3x plus 9. So I'm dealing with x squared plus 6x plus 9, right? That's not the same thing here. Okay, I've got an x squared plus 9. I have a 6x term right there. So be super careful. Remember what I always said, if you factor it out, take the 2 seconds to do a quick FOIL check to make sure that you get back to the original quadratic that you were working with. Okay, if you don't get back to it, then think of something else. Do the quadratic formula. If you do the quadratic formula on here, it's going to bomb out, right? You're just, it's not going to work. And then like here, or I can set it equal to 0 and I go to solve, I'm going to get a negative, right? Don't convince yourself you're doing something wrong. Just take a step back and take a look at what you're doing. Okay, I have an irreducible quadratic factor. I have to handle this situation differently. I'm really belaboring this point because I see this mistake a lot on tests and quizzes. You're rolling through really quick. You're trying to get things done. The partial fractions problems, take a long time. Okay, because there's like so much algebra involved just in getting it set up to do the integration. Okay, so it's going to take a long time. You're going really quick and you're not checking. Okay, so just take that 2 seconds to quick check and then take a deep breath and think about what you need to do. Okay, so let's talk about it. So let's rewrite this. Same steps that we've always done. We have to set up our partial fraction decomposition slightly differently than we have before, okay, because we have this quadratic now, okay, and I can't reduce it into factors, so I have to set it up as a quadratic. So I'm going to set this up. So my first step is I have to solve for my variables, and I'll write down what those variables are in just a minute. So I'm going to go 18 all over x plus 3 x squared plus 9. Remember, this is our first step, equals. I have a linear factor, so I can just go a all over x plus 3 plus. Now watch, I can't reduce this, so I've got x squared plus 9 in the denominator. The question is, what do I do in the numerator? Okay, I have an x squared term in the denominator. Okay, this is different than my linear factor that was repeated that I needed to write multiple times. Okay, this is an irreducible quadratic. I have to write it like this, bx plus c. Okay, you must write it like this. Remember, this is different than example 5. Okay, example 5 has x, what was it, like x plus 3 quantity, or x plus 2 quantity squared. Okay, that was different. That's a linear factor that's being repeated, has a multiplicity. Okay, this doesn't have a solution. It doesn't have a real solution. So what I need to do is I have bx plus c. Think about it like this. My denominator, right? My numerator needs to have something that has a degree less. It has to have you almost have to think about it like it has to be like a derivative, okay? Where this, right, a derivative from x plus 3 is going to be a constant term, right? It's just going to be like my coefficient of my x, right? That's a derivative of this. A derivative of x squared plus 9, I'm going to need to have some kind of I have to reduce, has to go down a power. We're not taking the derivative, but you need to think about it like what's in the numerator has to be a power degree less than what I have in the denominator. Okay, so I've got x squared plus 9. I have bx plus c in the numerator. Okay, so this is the format that I need to do. And now that means I have to solve for a, b, and c. So I have 3 variables that I'm working for here. Okay, so the process is going to be the same as what we've done before. I'm going to multiply top and bottom by this denominator. Here, x plus 3. X squared plus 9, both sides, so I can cancel out. Basically, I'm cross multiplying, so I'm going to get rid of my denominators. So I've got 18 equals a times x plus 3 cancels. I've got x squared plus 9. Plus, put parentheses around this right here because you have to be very careful because we have to distribute. Bx plus c now gets multiplied by x plus 3. Okay. Now, in this method, this is, remember when I said we have method 1 and method 2? I'm going to use method 1 because I've got a linear factor right here, but I must use method 2 in order to work with this factor right there. That's why we talk about it. Method 2 has to be used on irreducible quadratic factors. Okay, so let's go ahead and we're going to take our low-hanging fruit. So I've got this x equals minus 3 term here. So I can use that x equals minus 3 to help me solve for one of my variables. So I'm going to set that equal to minus 3. Everywhere I see an x, I'm going to plug in minus 3. So I've got 18 equals a times, I've got minus 3 squared plus 9 plus, this is bx plus c. This is going to be times 0. Okay, so I'm going to be able to solve for a. So this is going to be 9 plus 9. 18 equals a times 18. So then a equals 1. Okay, It happens in this case, if I have a linear factor, I can use this method here. It's good for like, it's a quick and easy way. It's kind of like low hanging fruit, okay? Method 2, I must use in order to solve for B and C. Okay, that's just how we have to do it because we don't have any other way. Okay, so let's just make a little note. All right, method 2, okay? So now what I'm gonna do is, I know I've got an x squared term, which means I'm going to remember how we have to pair up the coefficients of the like terms, okay, from either side of the equal sign. But on this side of the equal sign, all I have is 18. I don't have an x squared term or an x term. So I'm going to pad it with zeros. So I'm going to go like this: 0x squared plus 0x plus 18. Okay, it's kind of like a placeholder. It helps me keep it in place. You don't need to put the -3 into the bx plus c because you can, right? But we're going to plug in -3 right here, which is going to make it equal to 0. Okay, so let's do it right here. So now what's going to happen is I'm going to write this out. So I've got a times x squared plus 9 plus bx plus c times x plus 3. Okay, so the first thing I'm going to do is I'm actually going to multiply, right? I'm going to distribute out my a, and I'm going to FOIL this out. FOIL, and I'm going to distribute. Okay, so I'm going to go a x squared plus 9a plus, and we're going to FOIL this out. So it's going to be bx squared plus 3bx plus cx plus 3 times c. Okay, now what I can do is I have a, so I can substitute in 1 for a. That's going to make it easier. Now I won't have 3 variables here. I'll just have 2 that I'm working for. Okay, so if I substitute in 1 for a, basically I'm going to get just x squared plus 9a plus bx squared plus 3bx plus cx plus 3 times c. Okay, and this is still equal to this 0x plus 18. Okay, right, so all I did was substitute in a equals 1 right there. Okay, so now what we're going to do is we're going to start grouping things by terms, right? So I've got an 1x squared and a bx squared. So let's put that together. X squared plus bx squared. And now I've got an x and an x right here. I'm going to put those together. So I've got a 3bx plus cx. And then I've got my constant terms I'm going to put together. 9a plus 3c. Oops, sorry, 9a. That's actually, sorry, I could have substituted that with a 1. Let me do that now before I forget. Because a is equal to 1, so I can just substitute there. Okay, so 9 times 1 is just 9, and then 9 plus 3c. Okay, so now I've got these things here. So 0x squared plus 0x plus 18. So now what I'm going to do is I'm going to factor out my x squared. Okay, so I've got an x squared, 1 plus b. I'm going to factor out my x. So I have 3b plus c. And then I'm going to leave all my constant terms. Okay. All right. So now what I'm going to do, 0x squared plus 0x plus 18, I'm going to group these coefficients together. So the 0x squared equals 1 plus b. I'm going to set up, I'm going to have 3 equations and 2 unknowns, right? So I'm going to go 0 equals 1 plus b. This corresponds to my x squared. It's my first equation. 0 times x equals x times 3b plus c. So I'm just going to say 0 equals 3b plus c. That's my second equation. 18 equals 9 plus 3 times c. Okay, so I have 3 equations and 2 unknowns. I would have had 3 equations and 3 unknowns, but I had already solved for a, so I substituted in for a, and I can just solve for b and c. So some of these are going to be straightforward, right? This one's nice. So I'm just going to subtract 1, and I'm going to get -1 equals b. I'm going to subtract 9. 9 equals 3c. And then c equals 3. Okay. Straightforward. I didn't actually even need to use multiple equations, solve for it, and then plug it in, and then have to go back and resolve for it. Okay. So now I've done all the work ahead of time. So now I've got a, b, and c. Okay. Remember, all this was just set up so that I could solve for my integral and get this spot right here. So I'm going to start plugging back in my values for a, b, and c into here, and then we're going to work it from there. Okay, so this is our next step, which is step 2. put together. So let's remind ourselves we were doing this. This was 18 divided by x plus 3 times x squared plus 9 dx equals, right? So this is equal to a over x plus 3. So this is 1 over x plus 3 dx plus, right, this, b, so minus 1 x plus c all over x squared plus 9 dx. Okay, so this is what we're going to be integrating right here. Okay. Okay. I'm going to let you guys finish writing that. I'm going to turn the page so that I have more room to work. Okay. I'm going to turn the page. I'll write this over again. All right, so what we're dealing with was, let me just write this again so we can have it to look at. So this is 18 all over x plus 3 x squared plus 9 dx equals integral of 1 over, I'm just copying it, dx plus okay, so this is where we're at. So we're sorry, you can't see that. Let me get the camera. Okay, so now our step 3 is to integrate. Okay, so now we're in the realm of calculus. We did all our algebra to get it set up so that we could do the integration. Okay, so our step 3 is integrate. Okay, so let's think about what we need to. I'm going to integrate this part here. So this part's fairly straightforward. I can do u substitution on this. I'll write it in green. So I can do u substitution, right? So let's just write this out. So this is going to become integral of 1 over x plus 3 dx. Now what I need to do is I'm going to break this up into 2 different fractions. So I'm going to go x over minus x over x squared plus 9 plus 3 over x squared plus 9. Okay, so let's write that out. So I'm going to go, actually, let's do this. We'll just get rid of it. I'm going to pull the minus 1 out. This is going to be x squared plus 9 dx plus, and I'll take the 3 outside of my integral, 1 over x squared plus 9 dx. Okay, so all I did was I split this up into 2 different fractions. Okay, and then I brought the constant terms like my minus 1 and my 3 through the integral. Okay, and I'm going to integrate this, right? And then I'm going to work it from there. So let's talk about what we're doing. So this is plain, this is u substitution. We said that already. So I'll integrate that. So that's the natural log of the absolute value of x plus 3 minus, excuse me, this one right here. Let's talk about this again too. This looks like u substitution to me as well, because right, I've got x squared in the denominator, and my derivative of x squared is x. Right, I mean, it's 2x, but I've got an x is a derivative of x squared. So if I think u equals x squared plus 9, du is equal to 2x dx. Well, I only have a 1x dx, so I'll divide by 2. So I've got u equals this, and du over 2 equals dx. Okay, so basically what I'm looking at is I'm going to integrate this with substitution, and I'm going to get 1/2 natural log of the absolute value of x squared plus 9. I'm not showing all the steps for u substitution, just showing you the u and the du. Okay, plus now watch this, right? I've got a 3, right, that I'm factoring out. This here, this is our inverse tangent form. Okay, but the only difference is that our a value is equal to 3. Remember, we square, right? This is x squared plus a squared. Okay, and then a equals 3, so it becomes 3 squared is 9. Okay, so this is inverse tangent of x is this form that we're working with here. I have a 3 from before, so I have a 3 from before. And now the form for that, remember we talked about the generic form for the inverse tangent is 1 over a inverse tangent of x over a. And then don't forget your plus c. The 3's cancel. Let's clean this up and we'll put a box around it. So ln of the absolute value of x plus 3, don't forget your absolute values, minus 1/2 natural log x squared plus 9, absolute value plus 3 times 1/3 inverse tangent x over 3 plus c. And this 3 comes from our original equation. Okay, that comes from the c value that we found. Okay, has nothing to do with my inverse tangent. It comes from way back from the beginning. Okay. Be careful. The partial fraction problems are always a lot of work. There's always a lot of algebra to set it up. Okay, and you have to be very careful. These irreducible quadratics, right? You'll often get cases where it looks like you have a natural log and an inverse tangent function. Okay, so you're often going to end up with some kind of a trig when you have an irreducible quadratic that you're working with, but it may be in combination with a natural log, depending on like the nature of the bx plus c that you solve for. Okay. Let you guys finish writing that. And like I said, so that's the last example that I'm going to do in class. The example 7 is pretty complicated. There's a lot of stuff going on, but I will actually do that. I'm going to do that offline. I'll write down the solution for it before I scan it in, so you guys will have that. Okay. You'll have the solution for it. I'm just not going to cover it in class because it's more complex than what we will see in our class. This is always a possibility, this kind of a question here, because it combines a lot. So you should know how to do it, but example number 7 is probably more complex than you'll see here, but you know, it's good to know how to do it. Okay, guys. So that's the end of chapter 1.3 in terms of lecture examples and things that we're going to talk about. Okay, so the bulk of what we were trying to do happened in our lecture examples, okay, where we just went through all the different criteria, but the steps in the process for each were the same. Okay, we have method 1, method 2. Method 2 will always work no matter what. Okay, it's just more work. You have multiple equations and multiple unknowns. Method 1 will only work when you have a linear factor, okay, but it can be used in tandem in combination with method 2. Okay, so there's nothing wrong with using that. But you cannot use method 1 when you have an irreducible quadratic because there's no value for x that I can substitute in, or no real value for x that I can substitute in that'll make that work. Okay, guys? Phew, it's a lot of work, I know, but it's good. It's good skill. Okay, so keep on the lookout for the lecture examples for that later today. And then I put up an announcement online yesterday because I posted the homework solution problem for question 39 for 1.1b. You guys asked about that on Monday. It was, you know, kind of long and complicated, and it was also a lot like what we had done in class, but it had some nuances in there. But I posted it so you guys can see what that solution looks like. Why don't we take, you know, a couple of minutes before we move on to the next chapter section to talk about, which is improper integrals. Improper integrals, super important. We need to know how to process those. So we want to make sure we give ourselves enough time to think about it. But maybe we can spend, you know, five or 6 minutes answering questions for the homework. Remember, I have office hours today. So if you guys want to talk more about the homework, come to office hours and we can go through things. Any questions in particular on the office hours you guys want to ask about before we move on to the next chapter section?
For an unfactorable binomial in the denominator, like number 11, I had some trouble with that. I don't think it's factorable.
Sure. Let's see. For this is chapter 1.3. I think you're talking about.
Excuse me.
1.3 homework.
Yeah.
Okay. Yeah. Yes, exactly. So this is just like the problem that we just did. Do you want me to work through it, or are you
Oh, so it'll be the same steps, but it's
yeah.
not okay. Well, but okay. So I guess my question is, wouldn't it not be imaginary? Wouldn't the numbers be like from the quadratic formula? So why couldn't you do it like that?
From the quadratic formula? So m squared plus m plus 1. So what happens? So if you're not sure, so another way to see if it's going to work is I can plot it, right? So let me get rid of these here. So I can go x squared plus x plus 1, right? So I'm going to plot this out just to kind of see what this looks like. All right, so remember with the plots, right? So one of the things that happens with our plots is when the graph passes through the x-axis, or when it touches the x-axis, those are my real solutions, right? So my real solutions, right, tell me that I actually have x equals. Those are my x values that I can plug in and do method 1, right? Where I can say x equals this, x equals that, and then solve it. If my graph does not pass through the x-axis, that means I only have imaginary solutions for this, right? So I don't have any real. So even if I do the quadratic formula, it's going to come out imaginary, right? I'm going to get my discriminant's going to be less than 0, basically, right? Is what's going to happen. So I'm looking at this. So that means that I have to do method 2 to solve for it. So we can just set this problem up. So, so this is question 11. We'll just set this one up, right? Can you guys see that I'm switching to pencil? Is that still visible? So this one is, I've got 7m squared plus 12m plus 8. Now the difference is, right, now I have a whole quadratic in the numerator, so I have coefficients that I can set equal to when I solve for a, b, and c. And this is m plus 3. This is m squared plus m plus 1 dm. Okay, so how we need to set this up, I have a linear factor, which means I only use one variable, m plus 3, plus I have an unfactorable quadratic, right? Like, remember, if you're not sure, like, how am I going to factor this out? Well, I can't factor it, right? It's going to be hard to set that up. If I do the quadratic formula, I have to know what I'm looking for. What are the results I'm going to get that's going to tell me that I've got an unfactorable? And like I said before, like on the first day, your graphing calculator is your friend, because we're allowing graphing calculators. So just plot it and see. So it doesn't pass through the axis. So I know that it's unfactorable. So I'll make a note, unfactorable. So how am I going to set this up? That means I'm going to go, I'm using the variables a, b, and c. You guys are welcome to use whatever variables you want. Just don't use the one that's being referenced in the equation. So I'm going to use b and c here. So I'm going to go bm plus c, and I'm going to put that over m squared plus m plus 1. Okay, so now I'm going to set things up. I've got a linear factor here, so I'm going to go like this. Watch. I have to multiply both sides by the denominator, so I'm going to get 7m squared plus 12m plus 8 equals, right? This is going to be a times, right, because the m plus 3's cancel. Now put parentheses around this, bm plus c times m plus 3. Remember, because you're going to have to distribute it to FOIL it out. Okay, so the first thing I can do is, this is my m equals minus 3. That's one of my solutions. So m equals minus 3, right? I can plug in everywhere I see an m, I have to plug in a minus 3. So right here, I'm going to go 7 minus 3 squared plus 12 times minus 3 plus 8 equals, this one's going to go to 0. So this is going to be a times minus 3 squared plus minus 3 plus 1, right? And then this is going to be plus 0. That one goes to 0. Okay, so then when I work this through, basically what am I going to be getting? I'll find a equals 5 after I work it through. And I'll let you guys, actually go through and calculate, 7 times 9 and so on and so forth. So a equals 5. So that's method 1. That's going to make it nice because I can just plug in a equals 5 when I go to solve for b and c. Okay, do you want me to keep going on this one?
No, I think I could just run through it with the stuff we learned today.
Right. Yeah, try it. And then if you have problems on it, take a look. You can ask me in office hours, or we can go over it, at the beginning of class tomorrow, perhaps. For homework 1.3, number 14, do we do it like we did just now? So let me see, number 14. Let me look at my solution here. Oh yeah, so number 14 is an interesting one because it's sort of a trick. If you remember, so question number 14 is like, it's set up like this. So I've got 3 over r to the 4th plus 5r squared plus 4, and this is dr. And then what's going to happen is r, it's like one of those, we're doing a substitution. I think when we did it when you guys did this like in high school, like you probably did a substitution where you said n squared, like r equals, say n squared equals r. So then what was it? N equals r squared, say, for example. So then this reduces down to a quadratic, right? So this is like n squared plus 5n plus 4, essentially. And then you work it out, where like n equals r squared, right? And so then essentially, that's, you kind of do this substitution, right? So then that's how you end up getting to the 4th, because this is like a squared. That's how I got all these values here. So how this factors out is, it's going to look like AR, I called it AR plus C, and then I did R squared plus 4, like this will factor out. And then this was BR plus D. You can do this AR plus B or CR plus D. It doesn't matter what order, just keep track of where you're putting things. And this is R squared plus 1. So now I have two unfactorable quadratics, right? So this is unfactorable. This is unfactorable, right? And if I FOIL this out, I'm going to get R to the 4th plus R squared plus 4R squared plus 4. That gives me R to the 4th plus 5R squared plus 4. So I did a quick FOIL check, right? So I can factor this out to be R squared plus 4 times R squared plus 1, right? You can factor it like this to a substitution like we did in like, I don't know, algebra 2 or pre-calc, depending on when you covered it in high school, or you can just factor it out like this. So I get R squared plus 4 times R squared plus 1, and then I have two unfactorable quadratics, and now I must use method 2 for both, right? For all of these. So I'm basically going to get 4 equations and 4 unknowns. 4 equations and 4 unknowns. I'll give you the answer, explain how, yeah, I'll give you the answer and then we can talk about it. Oops, sorry, I'm losing my lead here. And then if you want to actually go over in detail about the method, I know it was just like what we just covered. So the answer, A equals -1, C equals 0, B equals +1, and then D equals 0. These are the answers that I got. And then my final answer that I got was -1/2 natural log R squared plus 4 plus 1/2 natural log R squared plus 1, and then plus C. This, remember, I put the absolute values on it just to make sure I kept myself honest, even though technically speaking, right, the values are always going to be positive, but just put the absolute value on it. I'm skipping the steps on how to do it because I want you guys to try it. But if you want to come to office hours, we can work through it in detail. But this is just like what we just did, okay, for our example. So try it out. Question 26. Let's talk really quick. And then we'll move on to the next chapter. Give me a sec to find it. Okay, so what's the question? How to approach it? Yeah, so question 26 is going to be like question 26 for chapter 1.1a. So this is, I want to be able to integrate. I've got 1 over y dy plus 1 over y squared plus 1 dy, right? So on both of these cases, right, this is my natural log rule. So this is going to end up being natural log of y. This is my inverse tangent. You're just going to have to recognize it as an inverse tangent. And remember, this is, you can think about this as y to the -1 dy. This one here says, right, if anytime I have my exponent is -1, that means I have to use natural log. So you need to be able to recognize, right, that you've got these special cases. I can't use power rule. And this is a trig function here. Like the trig ones that come up the most are inverse tangent and inverse sine. So make sure you've got those down in your mind when you recognize them here, okay, when I'm going to integrate. Like what's the derivative for inverse sine? What's the derivative for inverse tangent? Just like the one of the homework problems I think that we just took a look at, or one of the example that we just did, the a value, it wasn't x squared plus 1, it was x squared plus a squared. So make sure you remember the generic form of the inverse tangent or the inverse sine as well, so you can work that. Okay, so how to approach it? It's one of those things where it's going to take practice so that you start to remember and you start to recognize what's the natural log case and then what's the inverse tangent case. What should we expect for the quiz tomorrow? The quiz is going to be, the difficulty of the quiz is going to be like the difficulty of your homework problems, okay? And then what you can expect is like, it should take you no more than 20 to 30 minutes. I'm giving you guys 30 minutes to take it plus 15 minutes to take a picture and upload it to our Canvas page. So make sure that you guys have that time set up in your mind. I will create the problems so that they are doable within that time frame. Okay. If anybody has like a DRC accommodation where you get extra time, please email me offline so we can talk about how we approach that. Okay, with the quizzes and tests and stuff. Also, how do quizzes work? How are we going to be doing the quizzes and the tests? Because things are remote. Let's talk about that really quick. So we'll have our class tomorrow as normal. We may even end up leaving a little bit early so you guys, can have that time to, study or do whatever you want. The quiz itself will open up. Let's see, I think I have another class that gets out It's a Calc 2 class, and I'm gonna time it for them basically. So the quiz for us will open up at 3 o'clock in the afternoon tomorrow. And then it'll be open for 24 hours. So 3 o'clock on Thursday until 3 o'clock on Friday, okay? Which means you can start the quiz after dinner tomorrow night. You can start it, you know, maybe like at midnight, or you can start it tomorrow morning, or you can start it at lunchtime tomorrow, as long as you upload your solutions and you finish all your work, like you start it with enough time to upload your solutions before 3 o'clock on Friday. The availability window is going to close at 3 o'clock on Friday, which means that Canvas will no longer accept submissions at that point, okay? So when you do the quiz, it'll be like a download, right? It'll be one question quiz with a download. You'll download the quiz problems, and then you can print it out if you want to. You can work on the page that I'm sending you, or you can download it onto your computer to take a look at it, or just look at it on your screen, and then write down the question on your piece of paper. If you choose not to print it out, write down the question on your piece of paper, and then do your solution. Make sure you show me all your steps. Okay, do that for all the problems. When you're done, okay, at the end of your 30-minute time frame, take a picture, right? Make sure it's in PDF or JPEG format. Those are the only formats that Canvas will accept. And then you want to upload that into our Canvas page. There should be a spot for that quiz on our assignments page for uploading the quiz, okay? But you must upload it before the 3 o'clock window on Friday. Otherwise, Canvas won't accept it. So keep that in mind. You don't want to do all the work and then realize that you're outside the window. So that means that you should start it no later than 2 o'clock on Friday. Okay, give yourself plenty of time, you know, for the vagaries of, we have limited time to take it, or the full 24 hours once you open it. So it's a funny thing. It's an availability window on a timed quiz, right? So the availability window means that it's available for you to download like within that 24-hour period. After the 24-hour period, it won't be available even to download anymore, right? But once you start it, you have 30 minutes plus 15, right? We're adding that in, right? So the 15 is the time to take it and upload it. So 30 minutes to take the quiz and 15 to take a picture. And then the 15 comes from the math department, where we give people 15 minutes to do tech stuff, like take pictures and upload it to Canvas. But yeah, it's a timed quiz, right? But within the 24-hour window. So once you start it, you'll have 45 minutes to do it and upload your answers to Canvas page, okay? I know it's all really confusing because it's all really new, right? We're in an unusual situation. But normally, you know, in class, we would have done it like, we would have gone through some, you know, work in class lecture material, and then the last, you know, say 20 to 30 minutes of class, we would be taking the quiz. That's kind of how you want to be thinking about how it would work if we were in person. Okay, guys? All right, so enough said. Let's go ahead and move on to chapter 2.5. 2.5, 2.6, today and tomorrow material is not on the quiz tomorrow. It's on the quiz next week. The homework for 2.5 and 2.6 is due next week. The homework for this week is due by midnight tomorrow. Okay, so keep that in mind. There are 3 different homeworks that need to be uploaded by midnight tomorrow. Technically, it's 11:59, so keep that in mind. Okay, so chapter 2.5 is called Improper Integrals. And you guys, by the way, are free to email me if you've got questions about, like, you're unsure about how this whole quiz thing is going to work remotely. I can explain it again in email. Also, if you guys have technical problems during the quiz, you can email me. I'll try to be online, but you know, because it's a 24-hour window, I'm not going to be online the whole time, right? So, you know, try to get your answers and stuff. And I certainly can't talk about like content, right? How do you do certain problems once the quiz starts? So keep that in mind too. All right, so improper integrals. So first, I want to define, you know, let's do a quick step back. We're going to do a 1-page review on some stuff before we move on to actually how do we deal with improper integrals. Improper integrals is a super important topic because it comes up again and again and again in so many engineering concepts. When I studied engineering in undergrad, there were so many improper integrals that I had to analyze. So it's a really important skill for us, you know, especially as science and engineering majors, that we need to know how to do. Okay, so let's just do a quick review on a couple topics that are going to come into play when we're doing improper integral analysis. So let's remember about definite integrals. We're actually going to spend a lot of time this semester on definite integrals, but that'll be later, like in chapter 3. But remember, definite integral, I'm going from a to b. I've got bounds on my integral. And what do I get? I get capital F of x, and I'm going to analyze that from a to b, which basically our fundamental theorem of calculus says, right? I've got, if I go from a to b, I'm going to analyze it from a to b. That means I'm going to go f of b minus f of a is how I'm thinking about my definite integral. Remember, remember limits. Limits, if you were in my Calc 1 class last semester, we spent a lot of time on limit analysis, like how do we think about limits? Limits are a lot about convergence. We're going to use the idea of convergence with improper integrals. And with limits, it's all about whether or not the limit exists. Okay, and we need tests in order to figure that out. So let's remember our cases. We have 3 different cases for when a limit does not exist. When we've got 3 different cases. The first one, when the limit on the left does not equal to the limit on the right, right? It's somehow, or I'm going to get like my function comes into this value on the left, my function comes into this value on the right, right? So my left and right disagree with each other. On the left-hand limit, the right-hand limit don't agree. So the limit as a whole doesn't exist, right? So the left-hand limit will exist, the right-hand limit will exist, but the limit from both sides doesn't exist. The second condition for a limit not existing is when the limit oscillates at whatever value that we're heading to, right? So I'm not writing out limit as x goes to something, but it's going to look like my function goes, and then it starts going like this, like that. And this is the value that I'm looking for. So what's my limit on my left and my right? Well, the thing is, you know, it's going from -1 to +1, -1 to +1, over it's 2 minus 2, whatever. It's oscillating in values. It's not converging. It just keeps flipping back and forth. The second case on our limit not existing is where it's unbounded, right? So our limit goes to positive infinity or negative infinity, okay? The function goes up and it never stops. So we say that that's unbounded. Is the quiz being done the same way as your Calc 1 class last semester? Yes, definitely. So if you're in my Calc 1 class, it'll be just like that. Only it'll be Calc 2 topic, but the method that's being presented is just like we did last semester. For those of you who I had before. All right, another quick topic of review. Remember about L'Hopital's rule. L'Hopital's rule comes into play, right, when we're taking limits. But remember, we can only do L'Hopital's rule when we have indeterminate form. Right, so indeterminate forms, remember when I have 0 over 0, infinity over infinity, infinity plus or minus infinity, I've got 0 to the 0, I've got 1 to the infinity, infinity to the 0, so on and so forth. Anytime where you're going, huh? Is it 0 or 1, or is it 1 or infinity? What is this? You know, if you're scratching your head wondering about what it is, then it's L'Hopital. You should use L'Hopital's to help you analyze. So remember, L'Hopital says the limit as x goes to some value of a function over another function is equal to the limit going to the same value. And I take the derivative of the top and I take the derivative of the bottom. I don't do the quotient rule. This is derivative of the top. This is derivative of the bottom. And then I reevaluate the limit. If I still get indeterminate, I can keep taking L'Hopital's until it's not indeterminate anymore. Okay, quick review. We need these things in order to process improper integrals. So that's why we're talking about it now. Okay. So with that said, let's talk about what is an improper, like when do we use improper integral analysis? Okay. Remember, we're always asking ourselves, right? Like, I'm being asked to integrate some function and I have to go through some checklist. Can I do the power rule? Can I, can I do integration by parts? Do I have to use partial fractions? We're learning another tool in our toolkit. So when do we use improper integrals? So we use it in a couple different cases. The first case is when one or both limits of integration, right, our bounds of integration are infinite, right? So I'm dealing with, I've got like, I'm going to go some value a to infinity, right? Or I'm going to go minus infinity to a, or I'm going to go minus infinity to positive infinity. We do this a lot in engineering, right? We're looking at like steady state conditions. What happened before things started at 0 and what's happening at our steady state. So I need to kind of think about, you know, how am I going to do this? So I've got infinity somewhere in my bounds of integration. The other condition is because the function that we're integrating, f of x, right, has some number of infinite discontinuities on our interval a to b. So like, for example, like what does that mean, infinite? Infinite discontinuity is like a divide by 0 problem, right? So I've got like a vertical asymptote. So say, for example, just a quick example, I've got 0 to 1, and I'm going to integrate 1 over x dx. I should be able just to do the natural log, right? It's 1 over x, but I've got this, right? So that's going to give me a divide by 0. Okay, so this is a case where I need to use my improper integral because I can't just take the integral because I can't do the natural log of 0. It's undefined. So I have to have some way of analyzing that function. Okay, and my improper integral analysis is going to make that happen. Okay, so we're going to deal with this case first. Okay, we're going to talk about each of these 3 different conditions, right? And then we're going to deal with this case here. So we'll do part 1 and part 2. I guess we can call this part 1, part 2. Okay, so we'll do part 1 first. You guys all have this here? All right. Okay. Part 1. So this is infinite bounds of integration. Okay, so let's talk about in more detail, like what does that look like, and then how do we process it? You know, how do we think about it? And then what does it mean to, you know, take an integral of something that's going to infinity? Okay, so let's break this down into 3 different pieces. So the first piece is if our function f is continuous. And I should actually say part 3 is where I'm going to combine infinite bounds of integration with some kind of a discontinuity. But for right now, we're going to take them individually. So if our function is continuous on the interval a to infinity, right? I'm going to go to a to infinity. Then if I go a to infinity, f of x dx, how I set this up is like this. I'm going to say the limit of, I'm going to substitute infinity. I'm going to substitute this with, as b, some variable goes to infinity, and I'm going to integrate from a to b. Right, so this is how I'm going to process this. F of x dx. So I'm going to basically pretend like this is a normal integral, and I'm going to integrate it using, you know, my definite integral, my fundamental theorem of calculus. Only I need to analyze things as a limit because, you know, my b value looks like a definite number, definite value, but b is actually headed towards infinity. So I need to rewrite my function just like this. Okay, the limit is b goes to infinity, a to b, f of x dx. If you get a problem like this on a quiz or a test or homework and you don't write limit as b goes to infinity, you don't replace this and start analyzing it with the limit, you will lose points. Okay, so make sure that you are showing that you understand this is how we're processing an improper integral. So limit as b goes to infinity. Now what we're going to say is that the integral will converge. This is where convergence will converge when the limit exists. Okay, so if after I do all this stuff, if the limit exists, I say the integral converges. Integral is going to converge to whatever my limit is equal to. Okay, otherwise it will diverge. Okay, so if the limit does not exist, limit does not exist. Okay, we're going to go through lots of examples so you can see, but you must say, you know, like the limit exists, this is what a limit is equal to, therefore my integral converges to whatever that limit value is. Or the limit doesn't exist, it's, you know, unbounded, or it oscillates, or it's, you know, left and right are not equal to each other, therefore my integral diverges. These are all steps that you need to put down in the process as you're answering these questions. We'll go through examples so you can see. So first case like this, so the other two cases are tweaks on this, but let's write it out. If our function is continuous, now watch this, I'm going to go from minus infinity to b, right? So before my infinity was in the upper bound, now I'm going to start at the lower bound. So it's the same process here. Then what's going to happen is minus infinity to b, f of x dx equals the limit, and I don't care what variables you use, don't use x or b because we're already using them, as a goes to minus infinity of a to b, f of x dx. Okay, so what I did, look, I substituted on the lower bound, right? And now when I go to analyze the limit, I have to be aware I'm analyzing it as a is going to minus infinity. It's going to change the nature of my evaluation of the limit. So we're going to say the integral will converge when the limit exists. Otherwise, it will diverge. Okay, so the limit doesn't exist, the integral diverges. Does not exist. Okay, so upper bound is infinite, lower bound is infinite. Now let's do both. If our function we'll say minus infinity to positive infinity, right? So our function's continuous on this here. Then I've got this, my integral goes minus infinity to positive infinity, f of x dx, right? I need to substitute both, but I'm going to do them, I'm going to break them up into two different limits. So watch what happens. I'm going to go the limit as c, actually, well, first, let's first break this up. So this is going to equal to minus infinity to c, f of x dx plus c to positive infinity, f of x dx. Okay, sorry, this is a c, right? Where c is some value, right? And typically I'll do 0, you know, unless there's a discontinuity at 0. I'll use my c value here will be 0. It doesn't matter. Just pick some number that makes sense to you. Like I say, I usually like to use 0. It's an easy number to use. And now we're going to process this like I would for part 1 or part 2. Okay, I'm just going to break it apart so that each gets broken into a limit. So then this becomes basically, I'm going to go, it's going to go the limit as b goes to, or I can call it a goes to minus infinity from a to c, f of x dx plus the limit limit as b goes to positive infinity, f of x dx. I goofed. I needed to have a limit here, so that's goes right in there. Sorry about that. There. And what I'm going to do is just process it. Now, this function will converge if both of these, the integral will converge if both parts converge, and it converges to whatever their sum is. Okay, so both limits need to exist. If either limit does not exist, then the whole integral diverges. Okay, because I can't have infinity plus 5, right? That's going to make it, like if this limit here evaluates out to infinity, or the limit doesn't exist, infinity plus 5 doesn't equal 5, it equals infinity. So the whole thing's going to bomb out, the whole thing will diverge. So both pieces have to converge. Okay, so this would be 5 plus, say, 6, for example, and then my integral will converge to 11, say for example, okay? So you have to evaluate. Okay, guys? Looks like we'll be able to go through some examples here, and then we'll have to continue next time, which is okay. All right, so I've got my lecture example page for chapter 2.5. I'm just going to start working through examples so you can see, okay? And then we get to part 2. You know, we'll come back to our notes and then write more, and then we'll come back to our example page again. All right. So lecture examples. Example number 1 says, state whether the following integral converges or diverges. If it converges, state what it converges to. So this is a typical kind of question that you would see like on a test, for example. Because I've got 0 to infinity e to the minus x dx. So as an indefinite integral, e to the minus x dx, I can integrate that. It's just fine, right? But now look, I've got this, an infinite bound. So the first thing I need to do, I always like to graph these things out. It's going to look like this, right? So this, as x goes to infinity, goes this way. So what am I, you can kind of think about, like, remember our integral in this case is going to be talking about like the area under this curve, but this thing's going out to infinity. So what does it mean to take an area of an infinite, you know, to get a number for an area for an infinite area, right? How am I going to do that? That's why we're using this as a limit. So let me rewrite this. So I'm going to go the limit as b goes to infinity from 0 to b e to the minus x dx. My very first step, I need to rewrite this to recognize this is an improper integral, and I have to evaluate this using a limit. Okay, so now I'm going to integrate this normally, like I would with whatever rule I need. Do I need to use the power rule? Do I need to use exponentials? Do I need to use trig? Do I need to, you know, use integration by parts, partial fractions, whatever? You're going to use whatever tools you need to integrate this problem. I don't need plus c because I've got bounds on it, okay? So this is going to integrate to the limit as b goes to infinity. Don't forget, you're carrying your limit through until you are done evaluating. So the limit now is a part of your problem. So this, when I integrate this, I'm going to get minus e to the minus x, and I'm going to evaluate this from 0 to b. I didn't give myself enough room. 0 to b, okay? Which means this is going to look like, remember, the limit as b goes to infinity, because I'm still evaluating that. That's going to look like minus e to the minus, everywhere I see an x, I plug in a b, minus e to the minus 0. This becomes minus minus, this becomes plus, e to the 0 is equal to 1. So this is minus e to the minus b. What does this mean? So this is e to the minus b means I'm going minus 1 over e to the b. Okay, remember I have a negative exponent, means it needs to be on the other side of the dividing line. So the limit, this is minus 1 over e to the infinity. E to the infinity is a huge number, but 1 over e to the infinity, this thing goes to 0. And you must write this in, you must state what this is. So this thing goes to 0, which means I'm dealing with 1, right? Just have this 0 plus 1 is equal to 1. Therefore, I say this integral converges, and it converges to 1. The integral isn't equal to 1, but it converges to 1 because x is going out to infinity, right? And I have to be able to figure out what's the area of that. Well, that area is going to converge to 1 as a number, okay? All right, but make sure you do this. You have to carry the limit through each time until you're done evaluating it. You have to state what this is. As I plug this in, this is minus e to the infinity, right? So 1 over that, this goes to 0. I have to state that I recognize that that goes to 0. Okay. Okay, so then this one here, this looks like, I'm just going to do a quick graph. I like to graph these things out. So 1 over x, I'm only going from 1 to infinity. So I'm going to take a look at just this part right here. I'm not going to look at the negative x aspects of it. Just goes from 1 to infinity. So I'm looking at that. I like the graph just to kind of help me visualize. So let me rewrite this as a limit because I've got infinity in my upper bound. So I'm going to go limit as b goes to infinity, 1 to b. And this is 1 over x dx. Okay. This is x to the minus 1. That means when I integrate it, I get natural log, right? So this is equal to the limit as b goes to infinity, natural log of the absolute value of x right? And I'm going to evaluate that from 1 to b. Don't forget, you don't need the plus c because I'm evaluating this. Okay, so let's plug this in. This is equal to the limit as b goes to infinity, natural log absolute value of b minus natural log absolute value of 1, right? Well, I don't know, I'm not going to worry about this one just yet. I know what that value is, but this one right here, so this is the natural log of infinity, right? So the natural log function, is an increasing function, right? And as my value that I'm putting in there goes to infinity, this thing's going to go to infinity. This goes to infinity. So this thing is equal to infinity, which means that the limit does not exist, right? Which means that I'm going to conclude that my integral diverges because the limit does not exist. Okay, but you see how all the work I have to do, I must rewrite my integral as a limit process because I can't evaluate this using fundamental theorem of calculus with infinity. Infinity isn't a number, right? It's not a concrete number that I can plug in and work with, but I can evaluate as a variable approaches infinity, which is what we're doing here. Okay, so now the whole point is my integral will converge if my limit exists, and my integral will diverge if my limit does not exist. Okay. All right, we're going to keep working through examples here. All right, example 3. This is the typical how questions on tests and finals and stuff are worded. Does it converge or diverge? If it converges, what does it converge to? So I'm going up to infinity. That means right off the bat, I need to rewrite it. So I'm going to say the limit as b goes to infinity from 0 to b 1 over x squared plus 1 dx. And like I said, you can use another variable other than b. Just don't use x. You're already using x. Okay. So 1 over x squared, if I were to take that integral, you should start thinking right now, oh, that's a inverse trig function. Okay, that's going to be my tangent. So limit as b goes to infinity, I've got inverse tangent of x, and I'm going to go from 0 to b. Okay, so this is equal to the limit as b goes to infinity, inverse tangent of b minus inverse tangent of 0. Okay, which is inverse tangent of infinity. So we think right off the bat, we think, oh no, it's going to be infinity, right? Let's remember what our inverse tangent looks like. I'll draw it in a different color. Inverse tangent of x looks like this. Remember, I think we graphed this out the other day. I've got a horizontal asymptote at pi over 2, and a horizontal asymptote at minus pi over 2, right? And my inverse trig function cuts like this. Okay, so let's think about what's happening, right? So look at the graph. Inverse tangent of 0 is equal to 0. Inverse tangent of infinity, positive infinity, where does my function go, right? It's bounded on the top by a horizontal asymptote. This thing bounds to pi over 2. That's my horizontal asymptote. So this is pi over 2. So pi over 2 minus 0 is equal to pi over 2. My limit has a real number. That means that my integral converges. The integral converges to pi over 2. Limit exists. Integral converges to pi over 2. Integral is going to converge to what our limit is equal to. Okay, I think I've got time for one. The next one's kind of a long example. I think the next one's a long example. So I think maybe what I'll do is I'll stop here and then we'll pick it up. We'll pick it up tomorrow. We'll finish off the examples for 2.5 tomorrow, and then we'll start 2.6, and then we'll take our quiz tomorrow. Okay, guys. All right. Hey, I hope you guys have a great day and stay warm.
Thank you very much.
Okay, take it easy,
Thank
guys.
you.
Have a great day.
you.
Thank you.
Thank you.
Bye. Take care.
Thank you.
Bye.